Today we will try to derive the area of a circle of radius r. We will try to derive this using polar coordinate, but you can also do using Cartesian coordinate. The end result is same. As we all know, the area of a circle is given by pi r square, where r is the radius of the circle. This is a very small piece of a kind of a triangle which is formed by this line, this is small r, and this line, and we term this angle as a very small angle d theta. Let's say theta is the angle from the x-axis to this line. So, if we want to find the area of this complete circle, we can divide the whole circle into very small pieces of this triangle, starting from here. A very small triangle here, a very small triangle here, again a very small triangle here, and so on and so forth. The area of one triangle is given by half of length of the perpendicular and this base. If we assume that this arc is very small, then the length of this arc becomes equal to the length of the base of this triangle. So, the area of triangle OAB, we are writing a very small decimal area dA, and this is given by half of, when this BA becomes very small, then the length of this arc is same as the base of this triangle. And as we know, the length of this small arc is given by r into d theta, because we know that d theta angle is given by the length of this arc BA divided by the radius r. So this arc BA is given by r into d theta. So the area of this triangle, assuming that this arc is very small, is given by half into length of the perpendicular. If this triangle is very thin, infinitesimally going thin, and this line is approaching to this line, then the length of the perpendicular is same as this radius r. And the base of this triangle is same as this length of this arc, assuming that this arc has a very small infinitesimal length. So we term is as r into d theta. So this is the area of this small triangle. And from the integral calculus, we know that if we integrate it from the whole length, from as theta varies from 0 to 2 pi, then this will give the complete area. So area of this triangle, complete circle, is given by integral of dA as theta varies from 0 to 2 pi. So integration is nothing but dividing the whole thing into infinitely large number of pieces and adding their summation. That gives us the complete value of this integral, and that's what we are doing it here. In every problem of integral calculus which has a practical implication, we will find the value of one infinitesimal part, and then we add them all together, and adding them all together gives us the result of this integral, and that's the final result of this area. Substituting the value of dA, we get theta equal to 0 to 2 pi half r square d theta. and this r square is a constant, so we can take it out. If r, in this particular case, r is not depending upon theta, r stays constant no matter what the value of theta is, whether theta is 0, pi by 4, pi by 2 or any other value, r stays constant. In some of the problems, the value of the other variables will keep changing with respect to the independent variable, and then we will have to take into account and integrate it by substituting that value. So we can write it as half r square integral of d theta from 0 to 2 pi. So eventually this leads to half theta, as theta varies from 0 to 2 pi, we can write it as half r square into 2 pi minus 0, half r square into 2 pi, 2 gets cancelled, we get pi r square. So this is a simple derivation, and it also shows how we can use integral calculus to derive the area of a circle.